everyone. Thank you so much for joining us today. My name is Yanrong Xiao, and I'm very happy to welcome you to today's seminar, hosted by the USACM student chapters. Today, we are very excited to have Dr. Brayan Murgas with us. Dr. Brayan is a postdoc at Los Alamos National Lab, working in the X computational physics group. His research focuses on modeling how dislocation interact with grain boundaries in metal materials using field dislocation dynamics and crystal plasticity. With a background in the mechanical engineering and material science, he is specialized in how microstructure affects the mechanical behavior of materials and the effect of grain boundary properties during metal formings. He is interested in studying many physical phenomena across different scales, from atomic descriptions all the way up to the large-scale structures. And now the screen is yours. I will mute myself.
Yeah, Jaron, thank you very much for the invitation, and it's pretty nice that you're organizing the talks, and well, the student chapter is organizing the talks. So, I'm a postdoc in Los Alamos. I'm working with at XCP5, so it's the computational physics group in Los Alamos. So I'm working with my two main mentors, who are like Abigail Hunter and DJ Lasher. But I'm involved in other kind of scales. So like for Nathan Matthew and Avanish Mishra, they are working on molecular dynamics, so they're providing me some data for the work that I'm developing here. So the main ideas that we are developing this phase field dislocation dynamics. We're trying to improve the formulations, and one of the solutions that we found was coupling the phase field with micromechanical solvers. So these micromechanical solvers can, they have been developed like the last 20 years or even more, and you can develop like a small strain, large strains, like different things. And well, the phase field dislocation and phase field method is more like the evolution of certain variables and stuff like that. So the main goal here that we have in the group is how to upscale and do multi-scaling of the DFT and molecular dynamics data into this nano scale method, and maybe mesoscale for the crystal plasticity. So yeah, obviously, as I told, the main goal is to go up to the upscale systems and the large scale systems, sorry. And some of the tools that we use in the group are DFT, MD, phase field dislocation dynamics, and crystal plasticity. There are other people that work on disconnection phenomena, for the grain boundaries. So my main expertise or work is on crystal plasticity and phase field dislocation dynamics. And some of my colleagues are more into the atomistic and quantum part of the work. So I won't be able to give a lot of details about the MD and things like that, but I can give you the contacts or references if you are interested in that. So we do this multi-scale modeling for the grain boundaries because well, in the experimental setups, you can see that in the new for the new manufacturing methods, you can have grain boundary networks that are more complex and dense. So this is an example of a nanolaminate. So here before deformation, the grain boundaries are just vertical, and you can see that as the grain boundaries are more present in this material, you can have different types of deformation, and also based on the thermodynamic method that you are using, if it's as rolled or annealed, you can have different properties of your material. And what is interesting about these grain boundaries is that, well, they are defined by 5 degrees of freedom. So you have the misorientation and the normal. The misorientation is just an orientation that links two adjacent grains. So it's one orientation that will kind of fit one crystalline orientation to the other. And the normal is just the normal of the grain boundary. So you have for the misorientation 3, if you use a Euler angle parametrization, you have 3 Euler angles. And for the normal, it's a unit vector. So you have two additional variables. So it's 5 variables to define a grain boundary. And what is interesting about that is that when you compute properties of the grain boundaries, you can have different properties and tendencies of the grain boundary properties. This is an example of the grain boundary energy. So on the left, you have like a 1, 0, 0, and on the right, you have a 1, 1, 0 symmetric tilt boundary. So this 1, 0, 0 and 1, 1, 0, they just, for the misorientation, you are going to, it's like the axis of the rotation. And then misorientation angle is just like how apart are the rotation you are applying between one grain and the other. So the interesting part here is that you have for the grain boundary energy, and given misorientation angle, you have you can have different values of grain boundary energy depending on your normal, and this is because you have stable states, which are the ones in the bottom, and then you have metastable states, and this happens for most of the like spatial grain boundaries, like gamma 3, like gamma 7, and things like that. So you have different tendencies. So you can see that this one is like more is like kind of smooth, and here you have different cusps, and so this is pretty interesting because um, experimentally and using MD, we have seen like people have seen that that dislocations can actually transmit across the grain boundary, and this happens and this can change based on the first on the misorientation of your grain boundary, but also based on your if you are defined like if you are using a stable or a metastable state. So, so you can have different behaviors, like you can have transfer, like what you have here on the left, and you can have partial transfer, or you can have just like blocking. And this blocking of these locations at the grain boundary is what gives rise to the Hall-Petch effect, like the just like the yield stress kind of proportional to the grain size. And so we're trying to implement or like to yeah improve our continuum models. And what we want to do is like, okay, like we have all this molecular dynamics data, DFT. We want to compete, like improve our PFDD methods, and in order to be able to um, do the same simulations as in MD and improve our crystal plasticity models. So what I'm going to show you is like I'm going to explain what is the phase field dislocation dynamics formulation, and then I'm going to just go explain a little bit what is how I do the coupling between the phase field and the Lippmann-Schwinger solvers, and I'm just going to show some analytical results, and the most interesting part is like the grain boundary dislocation interaction. So you like maybe you're familiar with phase field, but phase field is just like we are using a variable that defines a phase, and for instance here you have two phases, phase 1, phase 2 on the left, and if you trace if you define like you see the phase field variable across this line here, this horizontal line. For the variable 1 you will have a value of 1 on the right, then it kind of drops and it goes to 0 on the phase 2. And this method has been used to model like crack propagation, grain growth. Now you have like a crystalline phase field or something like that, where you can define like the atoms and the lattice. And here what we are doing is that we use this phase field variable to define the plastic strain. So instead of this case, you will have like 0 for like a perfect crystal, 1 for a crystal that already undergone slip, and between 0 and 1 you have a dislocation. And this is like a kind of a classic definition of the plastic strain. And what we're doing is that, well, like we use fast Fourier transforms as like spectral solvers, and for that we need to define like our domains will need to be periodic. So this is kind of an example of what a simulation setup looks like for a heterogeneous material. So you have in yellow one phase, in blue another phase, and here in red you have the dislocation, like variable, the phase field variable. And when you see just the location variable, so you will see this kind of pattern here. So it's all like, as I said, it's periodic. You have periodic boundary conditions, and here our dislocations will be between the red and blue colors, because this is like the transition between 0 and 1. And so how I link the two of them is kind of like pretty simple like solver that I implemented. So what I'm doing first is that if I solve the Lippmann-Schwinger equation, this equation only like what it does is that we have the stress definition. So we have the total strain minus the plastic, and we apply the divergence of the stress. And for like the solvers of the Lippmann-Schwinger equation, they actually use the Green's operators. So you have a solution for your total strain in this form. And so what I'm doing is that I take this total strain and I use it to define the elastic energy for my phase field evolution equation. So you know that if I want to make the phase field evolve, I have to define these energy terms. So for this case, we have elastic energy, a lattice energy that is defining the kind of the resistance for a dislocation to slip your lattice, and then like you have the external energy. And so what I'm doing is that I take this total strain and I use it in the definition of the elastic energy, and the rest like of the parameters of the energy terms are just remain like that, remain intact. They are like kind of the classic phase field dislocation dynamics. So before this formulation, we used a virtual strain formulation. So this virtual strain formulation was a little bit different. We used an additional like evolution equation for virtual strains that were only defining the inclusions or in the heterogeneities of the material. But here I'm not using that. That just by like not using that virtual strain and kind of gaining a lot of time in the simulations. And yeah, so we started like after I set up the code and the solvers, we started to compare it with analytical cases. So it exists like analytical cases where you have only a matrix and a circular inclusion, but there are also like really nice analytical solutions for the same case, but with edge dislocations that are like inside the inclusion. And you can see if you want to check the analytical solutions in this reference. So this is the case where I have a software inclusion. So well, the solvers are like work pretty well for these cases. You may notice that we have some oscillations. This is because we are using FFT solvers, and this is kind of inherent of the FFT solvers. Then like I did the same for the harder inclusion, and the solution fits pretty well to the analytical solutions. I did softer and harder inclusions because we had a limitation in the virtual strain formulation for the harder inclusion case. So we wanted to make sure that it worked for both cases, and we overcame this like the difficulty in the previous formulation. So that was like a really nice thing to like be sure that it's working well. And now like the nice stuff, like how we are upscaling the grain boundary structures. So in this case, we are actually defining the grain boundaries as inclusions. So we need to define several like parameters to define this grain boundary region now. First, we need the width, but we also need the lattice of like we need to define the lattice energy of the grain boundary region, and also the stiffness tensor. So for the width, we are using a unsupervised Gaussian mixture model. So this was developed by some of my colleagues here in the lab, by Avanish and Nathan. And like the main difference here is that when you use a classical like method or like that are already like built up in Obito or something like that, we will have with like for this structure, like for this grain boundary, you will have this kind of grain boundary region here in white. But if you use this Gaussian mixture model, you will have a different grain boundary region. So they have shown that in this paper that this model works pretty well. Also, like they compare it with several cases for polycrystals and different things. So the main difference that what they are using here is that we use strain functional descriptors, and that's like what really makes the difference between the two models. And now after we define this grain boundary region, so now we have the width of my grain boundary region, and we apply a strain. So when you apply a strain, you can also compute the energy of your bulk region and your grain boundary region. And as you're applying like a higher strain in the positive or negative values, you will see that your energy will like kind of get farther away. So that kind of assures you that you are using that your grain boundary region is different to your bulk region. And so now, after we have this region, we can repeat this process of applying strains at different components. So you can apply different, like the different components such as X, Y, Z, but also like the shear components. And with this, actually, you can use second order elastic. You can compute second order elastic constants. So you can compute your energy and using like a derivative. I think it's a second order derivative. So you can compute the rest, like the remaining parts of your stiffness tensor. So we are applying this to compute the whole stiffness tensor, and is changes with respect to the bulk region. You can see this example here. You can see that the diagonal is different. Sometimes it changes more than other, like that in other cases, depending on the grain boundary structure. So the remaining like kind of ingredient that is missing here is now the lattice energy. So the lattice energy is kind of is pretty important here because we want to use partial dislocations. If we want to use partial dislocations, we are also using like the Fourier series approximation. So this lattice energy is like this gamma surface is computed or informed by DFT or molecular dynamics. And this is kind of important here because we use partial dislocations because the interactions between your grain boundary and your dislocation can change. Instead of like being like fully transmitted, you can have like your partial dislocation is actually like dissociating between a leading and a trail dislocation. So sometimes your leading dislocation can transmit and your trail dislocation can just get pinned, or and this changes a little bit, like not too many mesoscopic or mesoscale methods can do that. Like for instance, DDD can, I think they cannot do like partial dislocations, and so this is a kind of a main advantages here on the of the PFDD model. And so we have, in addition to the first one of the first slides where I show you the grain boundary energy changes for the metastable states, we also computed this for the same structures. We computed what is the dislocation interaction, and for these cases, like my coworkers selected different types of grain boundary structures, and they changed the misorientation and also the normal. So what they find out is that depending on your misorientation, you can have different reactions, but also depending on if you have a metastable or a stable state, you can also have different reactions for the same grain boundary misorientation. And this obviously changes as you apply a higher stress. So you can see that as we are applying a higher stress from 250, 570, 750, you'll have more fully transmitted or partially transmitted dislocations. So this kind of complexifies a little bit more the problem. It means that like we have to consider metastable states also, and also like kind of the dependency on the stress and dependency on the misorientation angle. So now like for the PFDD, we have the width, we have the elastic constants, and now what what is missing is that I need to also for the metastable states is kind of the main change is the grain boundary energy. So what we proposed was to change the lattice energy based on this grain boundary energy that you can see here. So we have a different lattice energy of the grain boundary that is proportional to the bulk energy, this term here, but multiplied by a constant that depends on the grain boundary energy. It's kind of a lot of energy terms. Sorry about that, but yeah, it's just like these ones. These ones on the left are like lattice energies, and this one is more like the energy of my grain boundary structure. So I'm going to show you two examples. We have this low angle and high angle grain boundary. They have different widths. They also have different elastic constants. So this is just the case for the isotropic cases. This is just isotropic cases, sorry. And these are the elastic constants of my grains. So you can see, for instance, for these cases that you have a softer grain boundary, but also a harder grain boundary. So you can see that for my the same material, you can have a different elastic constants, and that's kind of the two main like the main ingredients of your what a defect do is you change your elastic energy and your defect energy. So the defect energy is defined in this way, and my elastic energy is defined by changing these elastic constants. So so for the first case, we studied this 110 symmetric tilt grain boundary, and we have a 110 11. Oh, sorry, I don't see it well, but we have a different grain boundary plane. We have like a grain boundary energy of 751. We are applying a strain shear stress, and what you can see is that well, like we have dislocation that starts evolving towards the grain boundary, and sometimes like the dislocation kind of constricts or like kind of get compressed, and then after the grain boundary transmits, it just goes back to its original width. So this constriction is actually pretty often, like we can see it also in MD, and it always, like most of the time it does that, like it get compressed and then it decide, like the grain boundary decides where it's going, if it's going to remain pinned, it's going to collide towards the grain boundary, or it's going to get transmitted. So in this case, it just gets transmitted here. For the other case where we have higher grain boundary energy, different grain boundary plane and misorientation angle, you will see a different effect. So the grain boundary, the dislocation starts to approach the grain boundary, it gets compressed, but this time it gets like pinned at the grain boundary. So the main difference between this grain boundary and the present case is that this one has a higher grain boundary energy. So you can see that the effect of the grain boundary energy for a metastable state is can, like, we can predict that. We perform several simulations of from a grain molecular dynamics data set of grain boundary dislocation interactions, and we can like predict the behavior of several states. And one of the things that we need to do is that, well, like the conclusions that we did, like to wrap up here, like the resume the presentation, is that, well, we developed this new formulation, and we have good agreement with the analytical solutions, and we can reproduce the grain boundary dislocation interactions from MD. And some of the future work is we want to also simulate the absorption and the evolution in the grain boundary. So sometimes, as I mentioned, like the grain boundary can get compressed just in the interface between the bulk and the grain boundary, and then it, like the one of the like the leading partial dislocation can just glide along the grain boundary. And so we are working on that. We have already like all the tools to do it, so that's probably going to be finished soon. I'm using this lattice energy that is proportional to the bulk energy, but I think like we are working also on like the gamma surface calculation of the grain boundary, so that will like give us a better better like description or definition of our grain boundary region. And finally, well, we can use like a different way or a different methodology to define this grain boundary is by computing strain fields from MD and then use those strain fields as inputs in our phase field dislocation dynamics. I think this something similar was done a couple of years ago. And well, another, if you're curious, another way to do that is kind of compute the grain boundary dislocations and also compute the like use these dislocations as additional order parameters to describe your grain boundary, and we have done also that. And well, I think with this I can finish. I just wanted to thank you for your attention. Also, thank some of my colleagues for the discussions, and I'm open to have any questions.
Yeah, that's a great presentation. I have a quick question on slide number 3. I'm sorry, number 7, and I think number 8. Okay. Yes.
This too?
Yes. Yeah, concerning the geometry setup, I'm curious to understand how the setup, I mean, the diameter, the length basically influence the stress distribution near the inclusion. And then also, did you consider the mesh sensitivity or the boundary effects due to the domain size that I'm seeing clearly over there?
Oh yeah. So here, like the effect of the boundary conditions actually will be higher if you have a smaller domain. So that's why I'm using like a 124 like kind of grid, and every grid point is a Burgers has the dimensions of a Burgers vector magnitude. So it's kind of 2 Armstrong or something like that. And regarding so if you use also, it's the same thing. Like if you use a higher like bigger inclusion, this effect of your interaction. So you see that there is like a step here in the black line. So that will get reduced. Yeah. If you notice the literature, actually it's kind of funny because they use higher domains and higher inclusions, and they avoid a little bit that. So here is just an example. The diameter is 32, so it's kind of small compared to the domain size, but evidently you have an effect of that. Yeah. So this actually we are working on that mesh sensitivity and everything. We have done simulations, but we will publish this soon, so maybe you will see it later.
And
Thanks.
what type of inclusion are you considered modeling over here?
What type of inclusion? What did you mean? Like
I mean,
constant?
a type of inclusion you are modeling over. Is it a void or soft or like?
Oh yeah, so here is soft. So here, sorry, I didn't mention it here, but these are the constants, elastic constants of the matrix, and these are the elastic constants of the inclusion. So here is a softer inclusion. And yeah, and for the next one, for the other one, this harder inclusion. Yeah. So it's 2 times and just half. The other one was half.
Thank you.
Yeah, welcome. Thanks a lot for the question.
Sorry, one more time.
Yeah, no worries.
What type of software are you using for the? I'm curious to know. If you can't share, and if you think it's kind of something you can't share, that's fine. I just want to.
So I didn't understand the question.
Yeah, I'm asking the type of software you are using for this kind of simulation.
Oh, okay. Yeah, so actually this in-house code. So this is only like phase field dislocation dynamics. So the code is pretty simple to use. We only need like FFTW, the FFTW library. And that's a good question because I forgot to mention it, but this code is open source. So LANL, Los Alamos National Lab has a GitHub where they once they publish like papers, they also publish the source code of the paper. So so we have two versions already of the phase field dislocation dynamics. The first one is for homogeneous materials, and the second one is for heterogeneous materials using the virtual strain formulation. And this one that I use here is not published yet because we haven't published the paper, but I think it will publish like in 1 month or so. So it's going to be open source. So if you type like Lanol GitHub PFDD, you will see the versions that are already there, and you can use it and reach to us. And if you have any question or problem installing them.
Okay, thank you.
Yeah, you're welcome. Thanks for the questions.
Does anyone has more questions? We have plenty of time left. Well, I got one question. Hi, Brian, can you go to the slides 11? Yeah, this
Oh,
one.
this one? Yeah.
Yes, so for the example stiffness tensors, why are there some negative values?
Oh, well, the negative values are actually, how can I explain this? Actually, it's just mainly due to the definition of the directions that we are using. Like, I don't know how can I explain that actually, because I didn't compute this, but they are important, for instance, for the grains, because when you have negative values on the other side of your grain, it also kind of acts as it blocks the dislocations. So for our simulations, they are important to do that. We always consider them because they act as additional barriers of for the dislocation. So but yeah, I actually don't know why they are negative in this time, because I like it depends also in the energy. So if you check the computations here, like they are most of the time they are kind of they will have a positive value, but it depends on the structure of the grain boundary and and also on how they were defined, because like the grain will be like smaller or something, but I think it's mainly that it's like how we are computing it, and it's also with respect to our the force that we are applying, or the strain that we are applying. But yeah, they at least they are important. They are important for the reactions that we are obtaining.
Yes, I see. Thank you so much. And does this model sensitive to the mesh size?
So I think so. Like the things that will I haven't seen like too much sensitivity, because we at the end we are not applying like the only place where we are applying like kind of derivatives or stuff like that is for the Lippmann-Schwinger equation, but so you will have sensitivity here, but yeah, like obviously as we refine the grid is going to be like better. So for instance, these simulations here were performed with a kind of a coarse grid, so we only have like 32 points in grid points in the diameter of the inclusion, but if we refine it, this will be closer to analytical solutions. So
See, thank you. Great
yeah,
presentations.
yeah, thank you, Aaron.
Well, I also have some general questions. As I know, you have been doing research for a long time. Do you mention to talk about what motivated you to start interested in the research at the first step?
Yeah, so I think it was I think most of us are like I found inspiration from like teachers and other people I work with. So I remember, well, I'm originally from Colombia, and I had the opportunity to work in a little like research group. It was mainly like numerical and computational fluid mechanics and stuff like that. And I think I got attracted by it. By that time I just wanted to kind of learn how to code well and everything and things like that. And then I got like more involved into little research projects and that kind of uh, yeah, you know, like I started to get more curious about things like that. And when I finished my master's in France, I think I also worked with someone who was super nice, Stefan Verbeni in Metz. And yeah, it was, yeah, I think he played a big role also in my career. And he was super nice researcher, and I got also like into that with him. And but yeah, that's kind of the main main reason. Yeah, I enrolled the PhD later, but that's kind of the main reason I.
Yes, other than the encouragement from the good advisors, do you have some habits or tips to keep work efficiently and productively?
Yeah, so I think, yeah, I like always setting like schedules for my work. So for instance, here I'm working like in different projects. I have like more or less like 3 projects, so I know I kind of have to sometimes you have to prioritize based on your like your schedule and if you have conference and stuff like that. But besides that, I always kind of try to spend like an amount of time, like a given amount of time for every project. And yeah, so also one of the things that I encourage and advise to new PhD students and postdocs is always to do sports. That helps you a lot. Like at least that helps me a lot. So I think that's like a big game changer, just to also remain, if you have a sports or a passion about art or stuff like that, just always to keep it and don't like forget it, because that's also like important for everyone. And for me it's like cycling, and like, yeah, you know, that I was like rock climbing and stuff like that, or playing soccer. So I always like being active, and that helps me a lot to renew ideas and also like get focus actually. So that's.
Yes, that's great, especially for the tough topic like the phase field in the fracture analysis
Yeah.
with the green boundaries. And what do you think compared to other models would be the advantage of the phase field models, and what is the main challenges in the futures?
Yeah, so the advantages, sorry, I just wanted to go back to the well, you don't need, compared to some methods that where like for instance, I work with level sets for my PhD for grain growth. And when you compare these two methods, phase field and level sets, for the level sets you have a little bit more of dependency on the mesh. So I remember I used to do like dynamic remeshing for those simulations. That was like pretty hard, especially in 3D. And if you don't want to do that, you are always like kind of obligated to use like a more refined mesh and things like that. And in 3D, it gets more complicated because, yeah, like level sets, you have to do like reinitialization and other like steps that are like expensive. Phase field, you also have a mesh dependency, but I think you have as you are not like working on the mesh, you kind of have more like flexibility on that side. And one of the limitations is more like well, I think level, like the other methods will have it, is the dependency on the crystallography. So sometimes you have crack propagations that depends on crystallography. Here, especially for the dislocation dynamics, you have dependency on that. So you have to always be careful on your setup and things like that. But I know that there are like, I don't remember what is the correct name, but phase field crystal or something like that, where they really like define the lattice, and that's kind of nice because you will have like the lattice embedded already in your model. So that's nice. So there are like always solutions to the limitations anyway, but yeah, I think that's
Yes, that sounds interesting. And as you are working in the phase field as a postdoc in the national lab, how do you feel for your current work now?
I like it a lot. Yeah, I think, well, Los Alamos is a great place to work, and well, I like a lot working with Abigail and TJ, and they are super nice mentors, and the group is pretty dynamic. So you always have like well, like the group is pretty big, so you always have like someone to ask questions, and they are always like open to discussions, and it also feels like in a more kind of professional environment. It's obviously completely different to a university, but I feel is you have like a more the sensation or the feeling of working in a, like, maybe not in a company, but more like in a, yeah, like you're not just like a postdoc, you're also like part of like a team, or you're like always yeah, they like a lot the work that postdocs do, so that's pretty nice, and they always try to like continue it or improve it and things like that. So yeah, I think it's a really nice experience. I recommend it for people that are like thinking about doing a postdoc. I think it's a nice experience, and there are a lot of subjects like well, this group works on like this XCP5 has like different subgroups. We are in the material mechanics group, and but yeah, like theoretical division and other divisions have like more spread like projects from AI to I don't know, like environmental work. So you always have like a lot of different like research projects that you can also learn from. So that's pretty nice.
Yes, sounds like it is a great opportunities for you to work as a collaborators in the international labs.
Yeah,
Yeah.
yeah.
Yes, and what do you think is the main difference between work as a postdoc in the national lab and in the universities?
Well, that's a big question. So I think at least for my experience, I in the lab I've been more focused on my work. So so that I like that, like but I think it's, yeah, it's most like it's like what I feel is more like it feels more like as a like I don't know, I have the impression that sometimes in the postdoc way, like in the universities, you are more like just like you're not part of the, sometimes you don't feel part of the department, or like, and here I have the impression that you are more taken into account in several ways. So so it feels more professional in that way. So I like that. And also, like, yeah, like I think the national lab, you have a little bit more of benefits. If you are curious about that, you can also check that online. But that's like a big difference, I think. Like the salary and benefits are like a big difference. Mm.
Thank you so much. I hope this days national lab can have more openings.
Yeah. But if you are curious, you also can, yeah, like contact people directly. Sometimes yeah, like they have openings that they are not yet in on the website. Also, if you are going to be as USNCCM in Chicago, July, we'll have a booth. I will be there. So in case someone wants to go and chat with me about this work, or like how the like applying procedures work and everything, I'll be there, and I will be happy to answer any questions.
Yes, Brayan would like to communicate with you during the conference.
Yeah.
I actually have a question for you. It's a general question for the phase field dislocation dynamics method.
Yeah, sure.
So, since you're using phase field to represent two different materials, and since the function is smooth, you don't have a sharp surface between the two materials, right?
Yeah.
So, okay, in terms of this method, what is the interpretation for that range where your phase field value is between the value you set for the two materials? Because I think for this for the general physics problem you studied, interface is important, right?
Yeah. So the thing is that the interface. So let me go here. So so the thing is that the phase field only describes the dislocation. So like I can have multiple like fields, but here my phase field and my dislocation is actually just in the non-integer values. So my dislocation is between these two values, 0 and 1. And well, like the I know in grain growth and stuff like that, like they have like, or crack propagation, they have different like kind of methods and stuff for the transition between 0 and 1, but we don't use kind of like something special here. Like actually that's kind of a way we know the method is working or not. It's like if kind of if your dislocation is like going lower or higher than 0 or 1, you kind of know if things are working well or not. And like if you notice in this simulation here, so the dislocation, unfortunately, I don't have like a detailed view of the dislocation, but we don't have like if you see like, well, my dislocation is defined in my sleep system, and it doesn't evolve like outside this sleep system. So if you can see here, my sleep system is horizontal, and it doesn't go like to the two directions. So it's kind of, we kind of constrain it also in that way. And yeah, but I don't know if I answered your question, but
Well, kind of. Yeah, I'm also new to this method, so just curious.
yeah. But if you have like deeper questions, just also like you can send me an email. I don't know if I added my email here, but it's like you can see that my name in the thing in the screen is bmurgas, so is bmurgas@lanol.gov if you want to discuss later and how things. And if you are using Facefield, I'll be happy always to help with questions or things like that. So
Okay, thank you.
yeah, thank you.
It's nice presentation.
Thank you.
Yes, and I may have one last questions. Do you have any suggestions for current graduate or the potential graduate students?
Like suggestions, yeah. Well, I don't know. I think every career has its own like path and rhythm. So yeah, like think yeah, like I think you just need to follow like what your gut is telling you, and yeah, like I don't know. I have the impression that it's pretty difficult to give advice about that, but I have to repeat that, like if you have any other passion besides research, just continue doing it. Don't forget it. That's super important in your life. And yeah, I think the work, and always do your work with passion, a lot of commitment. That's something that will always help you open doors everywhere. But yeah, I think that's kind of the general advice I have. I'm not also like too experienced to give a lot of advice on that. So
Yes, but I do agree to keep passionate towards your research. Thank
Yeah,
you so
yeah,
much.
yeah.
Does
Thank you
anyone
very
has more questions? Well, thank you all for attending these presentations, and thanks to Brian for giving such a wonderful talks. And nice to see all of you. Bye.
Well, thank you, Jaron. Thank you, everyone. Have a good day.